Standard electrode potentials. So the standard electrode potential depends on the two half reactions that are in the cell, and it measures the difference in potential energy between the two electrodes. So we can think of each electrode as having its own potential, the standard electrode potential. And then the standard cell potential is the difference between the standard electrode potentials. That makes sense? Maybe? So here we have two, these don't look like water tanks, those look like beakers without spouts, but whatever. Here we have two containers of water connected by a common pipe. The water is going to flow, of course, from the tank with the higher level to the lower, because this has high potential energy and this has low potential energy. With an electrochemical cell, the electrons are going to flow from the more negative charge, the one that has the greater potential energy, to the electrode with the positive charge, which has less potential energy. That make sense? As with several other quantities that we've encountered in Chem 1A and Chem 1B, the electrode potential in a half cell cannot be measured directly. So we've assigned 0 to a particular type of half cell, and we measure everything else relative to that. Again, it's like altitude, we measure relative to sea level. So what we're measuring relative to is C, standard hydrogen electrode. And here's a picture of it. So there's a tube here, and we've got hydrogen gas being pumped in here at a pressure of 1 atmosphere. So that's the standard concentration, right, for a gas. And down here we have a platinum electrode, and this is a 1 molar acid solution, so also a standard concentration. So the reaction that's going on here is 2 hydrogen ions are reduced to H2. And so we have decided that that's 0. So then you can use this, connect it to another half cell, and then you can figure out what that one is, right? Does this look like a real convenient electrode to use all the time? No. Because you got hydrogen bubbling out here all the time, right? Hydrogen's rather explosive. The Hindenburg, yeah. So I don't know that I've even ever seen a standard hydrogen electrode. But that's what everything's measured in relative to. Okay. So here we have zinc being oxidized to zinc ion. This is the oxidation. And over here we have our standard hydrogen electrode, She. So the voltage difference between these, because this one is 0, is going to be the potential for this. So E cell, and again we're looking at difference in voltage, is the difference between the final and the initial. So this is the initial and that's the final. And the book is very nice and consistent. They always put the oxidation on the left and the reduction on the right, and that's how the line notation is. But if you turn them around or look at it from the other side, this number won't change, obviously. So they do this. I don't particularly like it. It's the cathode potential minus the anode potential. So the cell measured there at 0.76. So we can assign the electrode potential because we're measuring it relative to the standard hydrogen electrode. So it's the potential of the cathode, which was 0, minus the potential of the anode is equal to 0.76. Because that's what it said. Oh. So the potential here is 0.76. If we switch the leads, then it'll be negative 0.76. But over here, solving this little problem here, that means that the anode potential must be negative 0.76 volts. So we have oxidation occurring here, and the half reaction for that oxidation is negative 0.76 volts. That side has a more negative electrode potential, so that's greater potential energy of an electron at that electrode, and the electrons are going to flow away from that because it's negative. Here for a copper 2+ electrode, the measured cell potential would be negative 0.34. So here, this one is more positive than the standard hydrogen electrode. So it has lower potential for an electron. The anode then is at a more positive voltage, and electrons are not going to flow to the cathode. Because the more positive the electrode potential, the lower the potential energy. I really don't like these slides. See, we're going to get to this. That's the good stuff right there. So the copper electrode is positive relative to the standard hydrogen electrode, tends to draw electrons away from it. The zinc electrode was negative and tended to repel electrons toward the standard hydrogen electrode. So when we put them together, electrons are going to move from the zinc electrode to the copper electrode. By convention, standard electrode potentials are always written for reduction half reactions. So this is the reduction half reaction because reduction is gaining electrons. So the standard reduction potential here is 0.76. For copper being reduced to copper metal, it's positive 0.34. Okay, so there's this great table. Let's look at it for a minute. That's part of it. That's the other part of it. Didn't fit on a slide. This table shows us a whole bunch of reduction half reactions. And it gives their standard potential. Okay? So when we're looking at an electrochemical cell, we have one reduction half reaction and one oxidation half reaction. Right? And so what the book does is they do this dumb thing where, you take the potential for the cathode, written for reduction, minus the potential for the anode, written for reduction, and I can never remember which one comes first. So this is what makes sense to me, and I hope it'll make sense to you, because this is what I'm going to do the rest of the chapter. So here, if we reverse the half reaction, make it oxidation instead, then what do we do to the cell potential? You reverse it, change the sign, right? So if this being reduced is negative 0.76, this thing being oxidized would be plus 0.76, right? So here, it's plus 0.76. So we're not paying attention to this one anymore. And this makes a lot of sense to me because that's what we did with delta H, delta G, right? The one thing you have to watch out for is if you multiply this half reaction by a number, you don't multiply cell potentials. The cell potential is just the cell potential because this does not depend on the amount of zinc present, right? Standard means it's 1 molar this, and whether you have 5 liters of it or half a microliter of it, the potential's the same. So then we can take these two half reactions and add them together. And we're just going to add the cell potentials, the electrode potentials. Does that make sense? So what you do is you look up the half reactions you need in the table, write them down with their potentials, and then flip the one that you need to be oxidation, change the sign on the cell potential, add them together. You don't even really need to be that conscious of which one's the anode or the cathode.
So whichever one's the more negative can flip?
Well, it depends on the problem. If they're, this would be spontaneous, right, because it's generating electricity. To do the other, for the standard cell potential to be negative 0.76, we'd have to use a battery or something to make that happen. So, but if they, give you something like that happening and say, well, the hydrogen is being oxidized, well then you reverse the hydrogen.
So they'll give us like an equation like this?
They could, yes.
Okay.
Mm-hmm. So that's our table. And students, I just don't even know how to think about this. Students will ask me questions like, do we need to memorize that? No. You were having trouble with the element symbols, right? No, you're not going to memorize that. Do we need to memorize the vapor pressure of water at different temperatures? No, absolutely not. So please don't ask me that.
Do you have all of, most of these memorized?
No. I know that she is 0. That's about it. Yeah, that's about it. Oh, I was going to say something. So this is low tendency towards reduction. This is high tendency toward oxidation. And up here would be low tendency towards oxidation. And this would be high tendency towards reduction. So the electrode potential of the SHE is exactly 0 because we defined 0 as that. Electrode with a greater tendency towards reduction will be positive relative to that. With less tendency towards reduction, it's going to be negative, meaning the spontaneous direction would be an oxidation. Again, they insist on this, the cathode minus the anode. This is probably the best thing on this slide. The cell potential is positive for spontaneous reactions and negative for non-spontaneous reactions. Okay, so let's calculate, let me peek, no, I didn't do that, that would be too simple. Use tabulated standard electrode potentials to calculate the standard cell potential for the following reaction occurring in an electrochemical cell at 25 degrees C. The equation is balanced. So it's nice of them to tell us that. So we're going to have to look up some cell potentials here. So be thinking about what are the what are the half reactions in there? Come on, there you are. Can't see. Well, lead ion is going to lead metal, right? That doesn't work. 3Pb2 plus, aqueous, is going to 3Pb solid. There's got to be some electrons involved there, right? So we're going to have some electrons over here. And then we've got 2 chromium going to 2 chromium ions. And that one's going to have the electrons over here. But not 1. And not 2, but 6. Okay? Excuse me. Okay, so what we want to do is we want to find lead 2 to lead the element in the table. I must be allergic to this book. So, looking around here, and this is what I find. Okay, and then I'm going to look for chromium, and you have to be careful and make sure that both sides match, because the chromium 3 can go to chromium or chromium 2, and here we want it to go to chromium, so it shows me the reduction half reaction. That's negative 0.73. So note to self, take a picture of that in the book and paste it in there. So obviously this one is the most like this half reaction, right? We've got some coefficients here, but this is the cell potential. This reaction is written in the same direction as the one in the table. So we're going to just copy in E0 equals negative 0.13 volts. This one, if you disregard, if you divide everything by 2, is this half reaction, but in the other direction. So we're going to change the sign on E. So here, E0 is not going to be negative 0.73, it's positive 0.73. So you look up the half reactions in the table, and if your half reaction is reversed, you change the sign. And then you add them together. I don't trust my brain today. So negative 0.13 plus 0.73, 0.6. So positive 0.60 volts. That's the cell potential. Any questions? That's not too hard, is it? Because personally, I don't really care which side's the anode and which is the cathode. I'm looking at a chemical equation. I'm not looking at a cell, right? So we don't need to think about that. So 0.6 volts. So an electrode has a negative electrode potential. Which statement is correct regarding the potential energy of an electron at this electrode? An electron has lower potential energy than at the standard hydrogen electrode. It has a higher potential energy or the same. Well, obviously the same is not right. It's not that one. So this is, he's got the answer. It has a higher potential. How do we even think about that? Well, how did you think about that?
If it's more negative, they want to go.
So it wants to go away, yeah. So the electron, that electrode has a negative potential, and the electrons go away from the negative to the positive. So that's why this one is correct. Any questions? That's not the kind of question I like to ask on an exam, just in case you were wondering. So, predicting the spontaneous direction. So what you're going to do is you're going to compare, you're going to look at the standard potentials for each half reaction. And find the standard cell potential. A spontaneous reaction has a positive cell potential. And so, I mean, this is true. Any reduction half reaction is spontaneous when paired with the reverse of a half reaction listed below it in table 20.1. That's nice. I don't think of it that way. Negative charge repels electrons. Electrons move away from the more negative to the more positive. Oxidation is loss of electrons. Oxidation occurs at the anode. How do you find the standard cell potential? You look at the two half reactions involved. The one that's flipped, you change the sign, you add the two numbers together. I guess, if you can remember, the oxidation below with the reduction above is spontaneous. I suppose that's faster, but I never remember it. So then that doesn't help. And electrochemistry was what I studied in graduate school, so I just haven't done it for a really long time. Okay, so here we go. We're predicting the spontaneous direction. So what do I need to do to get a cell potential that's positive? Should I flip this one or that one? I want to flip this one, right? Because it's bigger and it's negative. So it's not actually asking us to calculate the cell potential, it's just asking us to predict the direction of the oxidation reduction. So the manganese is going to lose electrons, right? Oxidation is loss of electrons. Oxidation and anode both start with a vowel, right? So the anode is the manganese side, and the nickel is the cathode side. So it's going this way. Because this one looking at reductions, this one is more positive and that one's more negative. That just doesn't work for me.
Did we have to flip it? Like,
Well, you don't actually have to write it out.
we said that the manganese one was more negative, right?
So what the book is telling you is whichever one is more negative will be the anode,
Yeah.
and the more positive one will be the cathode. But if you want to know what direction it's going to go, you figure out which of these is going to be oxidation by looking at what's going to give me a positive cell potential.
Can we just say that one's more negative, so electrons go away from that one?
Yes.
Okay.
Mm-hmm. So without calculating the cell potential, predict whether the redox reaction is spontaneous, sketch the cell. Okay, so just a word of warning, you will be asked to sketch an electrochemical cell, okay, on an exam. So just be aware of that. Label the anode on the left, the cathode in the direction of electron flow. So here we have zinc and nickel, right? So here's nickel.
Does it have the values in it?
No, it doesn't have the values in it. So here's nickel, and zinc is here.
Oh, but we use like Electrode.
Yeah. So these are positive up here and negative down here. So zinc is lower. It's going to be more negative than the nickel. So if I flip that one, I'm going to get a positive cell potential. So this one's going to be the oxidation, that one's going to be the reduction. It's not complicated at all. Not confusing at all. It's hecka confusing. Yeah, so the potential for this one, which isn't actually listed here intentionally, is more positive because it starts with positive at the top and it works to negative. This one is more negative. So the book's method is to say, well, the more negative one, the electrons are going to run away from, right? And then I forget. So that's going to be the anode. That's going to be the oxidation. That's the one that's flipped. But if I take a more positive number and I change this more negative number to positive, then when I add them together, I'll get a positive number. Even if these are both negative, that one's less negative than this one. So is this, as written, spontaneous?
Yeah.
Yeah, it is. So we've got our salt bridge, And we've got some electrodes. This is the anode. This is the cathode. So the zinc is losing electrons. So the zinc is over here, its electrons are going that way. These are connected by a wire with a little meter in it. So electrons are moving that way. So this is the zinc, the solid zinc, and this is where the zinc ions are. Over here, this is the nickel electrode and the nickel ions in solution. And sometimes you might have to actually write salt bridge. Any questions? So this is going to give us a positive voltage here. It's spontaneous. Is the following reaction spontaneous under standard conditions? Well, we've got zinc and zinc 2+. And we've got calcium 2+ and calcium. Well, I thought of something that makes sense to me. This guy's on top. Somebody has to switch, go backwards. This guy's on top, he doesn't have to switch. The guy underneath him has to go backwards. Now that makes sense to me. So spontaneous, this is going to be the oxidation, and that's going to be the reduction. This is going to go as written, this is going to go backwards. So is that what's happening here? We have zinc ion going to zinc. Now we have zinc going to zinc ion. And we do have calcium ion going to calcium, but we decided that because he was lower on the totem pole, he had to switch. So that's also backwards. Both of them are backwards. Is this spontaneous? No. Any questions? Solution contains both sodium iodide and sodium bromide. Which oxidizing agent could you add to the solution to selectively oxidize the iodide but not the bromide? So we're going to look at relative positions. So let's find iodide and bromide first. There's iodide and there's bromide. We're wanting to oxidize them. These are reduction half potentials. So we need them to flip, right? So we're looking for something above them on the table. But we want to do the iodine and not the bromine. So that means we want to look in this region between. Because anything under bromine will not oxidize it. But these guys will all oxidize iodine. H2O2, HNO3. There, H2O2. Sometimes you have to, search around because the thing you're looking for, depending on whether it's oxidizing or reducing, could be on either side. So you could use hydrogen peroxide to oxidize iodide but not bromide. If you use something up here, what's going to happen? Wait a minute. That's the only one that's in between, isn't it? If
Well, I think if the iodide is flipped, then it wouldn't,
the H2O2 is on the wrong side,
Yeah.
right? Yeah.
But NO3 is on the right side.
See, I somehow couldn't see NO3. What made me realize my mistake is when I caught a glimpse of this guy up here. Like, wait a minute. That's a reduction reaction. But it's not H2O2 being reduced. So here we have the nitrate ion. This will be reduced, oops, this will be reduced, it will oxidize that. Again, I wouldn't put a question like this on the exam. They're useful though, because they make us think about it, right? If I use peroxide, now that I've opened my eyes, that would oxidize both the bromide and the iodide. Okay? Thanks for catching that, Scott. Predicting whether a metal will dissolve in acid. Some metals dissolve in acid and others don't. I don't know if you remember experiment 2A in Chem 1A, where you took the copper wire and you stuck it in nitric acid and it dissolved, right? But not all metals dissolve in nitric acid. And some metals dissolve in hydrochloric acid, but copper doesn't. So the way the acids dissolve metals is by reducing hydrogen ion from the acid into hydrogen gas, and that's what the bubbles are that you see. And you get the oxidation of the metal to its ion. So here we have the oxidation of zinc and the reduction of hydrogen ion. So to predict whether this is actually going to occur or not, we look at, is the cell potential positive? Is H plus above Zn plus on that table? So metals whose half reaction reductions are below H plus will dissolve in acids, except copper. Do I have the table? Just so many letters and superscripts and subscripts. This is not pertaining to the question that's being asked on this slide. But here's the reduction half reaction for copper. For it to dissolve, it's going to be oxidized. So this one needs to flip. That one needs to reverse. And we compare to the hydrogen ion. Which is not on this part, is it? I think it's below. Let's go back to the whole table. There's hydrogen. Right. So all of the metals below it will dissolve in acid. Copper is above. It will dissolve in nitric acid and only nitric acid because the reaction that occurs is different. It's not this one. It actually uses the nitrate. So which metal will dissolve in nitric acid but not in hydrochloric acid? So the HCl would be the H plus, which is the zero, the standard hydrogen electrode. And HNO3 is right there. And so we see that copper is below that. So are any of these others in that area? Looking over here. Well, this is Fe2+, not Fe. Silver. Silver will also dissolve in nitric acid. And here's gold. Gold is really quite inert. There's only a few things that can oxidize it, which is one of the reasons it's really good for jewelry.
Why is HCl listed?
So it's a bad slide. So this is the whole table. That's the top of the table. This is the bottom of the table. And this is the equation that all the other acids do. It's the hydrogen ion that causes the metal to become oxidized. In nitric acid, it's not the hydrogen ion, it's the nitrate ion. So nitric acid will also dissolve all of those.
Is that the same thing as like sulfuric acid and other dihydroic acid?
Yeah, so sulfuric acid would dissolve iron and lead and tin and nickel, etc. And if you had a weak acid, it would still dissolve it. It just might take a while.